Welcome to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Adam Klett.
All right, welcome everyone. Thank you, William, for the introduction. Today we're going to be talking about intentional contamination for quantitative cleanliness studies in this Tech to Tech series. And if you're asking yourself, why are we trying to intentionally contaminate our circuit boards? Well, I hope by the end of this presentation, I can convince you that there are some scenarios where it might be useful, and then give you the tools that you need to be successful in your own ventures. So I doubt that anyone would argue with me when I say that cleanliness, especially of high reliability assemblies, is very critical to prevent failure due to various electrochemical phenomena. For example, the formation of dendrites or calf or corrosion. And to help us figure out that we've cleaned our boards well enough, we have tools that we've developed like ROSE, IC, C3, and SIR. Right? And those have worked out great for us. However, I'm going to argue that none of these methods actually directly quantify the contamination present on the board. For example, ROSE measures the resistance of an extract, right? So the assumption there is that everything was extracted from the surface of the board. IC also measures elution times of an extraction solvent. SIR goes even further and doesn't even measure that. We were measuring surface resistance over time. And then C3 again is another extraction method where we're measuring the electrical current conducted through the extracted solvent over some period of time. And so these measured properties are quantified, but then they're correlated to predetermined pass-fail criteria, not of a surface concentration or contamination. For example, no one says that an SIR value of 9.5 log ohms means that I have 12.2 micrograms per inch squared of contamination on my board. Right? So these acceptance criteria are not based on a quantified value of contamination, nor are they determined on a product by product basis. Now, that would be very difficult, and I'm not proposing that that should be the case, but instead, these acceptance criteria have been collectively agreed upon as an industry, us, and written into standards or widely accepted literature. And so you can imagine that, for products or processes that have already been developed, that might be fine. Those criteria have worked well in the past, and they continue to work. But for next generation products, those criteria might not be sufficient. For example, consider products that incorporate new packages with different geometries, or maybe smaller components or denser designs. Right? A method for creating samples with known uniform levels of contamination might be needed to meet the higher demands of future designs. So what kind of methods do we have to intentionally contaminate our boards? Well, luckily, we don't have to go very far in the literature to look at other industries to see what we can do. In this work, we're going to focus on one of those methods, which is called spin coating, to demonstrate that ability to uniformly coat a PWB surface with a precise quantity of contamination. Now, note that there are two parts of that. The first part is the uniformity. We want to make sure that we get the same exact amount of contamination across the entire board. And the second is a precise quantity. We want to be able to pick out exactly how much contamination we want to add and spread that evenly across the board. And this will help with qualifying new or established methods if we want to go back. And it'll also help support the determination of that question that we all have of, how clean is clean enough? So how are we going to make these contamination solutions? So you have two options, different types of contamination. The first is going to be ionic contamination, or you can choose to work with organic contamination. A lot of times, ionic contamination is looked at as a culprit for a lot of those electrochemical failures. And so in this work, we are going to demonstrate this, this procedure with sodium chloride dissolved in methanol. We're going to measure and make our calibration curves with C3 and IC tests. But on the other hand, we do have inorganic or organic contamination that may be present, things like silicones, which cause issues with bonding, can be wire bonding, adhesive bonding, conformal coating applications, where silicones are an issue. And so the second round of tests that we did here was PDMS, or polydimethylsiloxane, dissolved in hexane. And to quantify those calibration curves, we use FTIR. And the solutions that we made were made specifically to target a surface concentration of interest In this case, about 10 micrograms per inch squared. And that's a typical level that we, around the limits that we see for these applications. All right, so how are we going to do the spin coating? Well, spin coating equipment is commercially available. You can go online, and there are various items out there ranging anywhere from, a few $100s to a few $1,000s. If you don't have spin coating equipment, or you don't have access to spin coating equipment, you can carry it out with a modified stir plate, which is what I'll be showing here in this example. Here in this work, we used a modified stir plate where we removed the ceramic plate off the top, and then we custom 3D printed a chuck to interface with the spinning magnet, as you can see in the diagram to the right. And then you can see the sample board clamped into the to the chuck there. So after we figure out how to actually make the boards, we need to figure out how to analyze them. We decided to use 3 different methods: C3, IC, and FTIR. So in the picture in the middle, you can see the spots represented by the white circles, which show the areas where the C3 was carried out. So C3 was carried out in each of those areas. The corrosion index was measured on the extraction solvent, and then that same solvent was carried over into an IC vial and analyzed via IC. Now, for the silicone measurements, the boards were covered and then measured via FTIR, ATR, and you can see the circles on the figure on the right representing the areas where those measurements were taken. Now, it's important to note that we measured the FTIR on the pads and not on the solder mask, because the solder mask has its own FTIR signature that could make the analysis complicated. Also, it's important to pick a peak when you're doing the FTIR analysis that's assignable only to your contamination. So when we did so, we made sure that the peak that we quantified could not be found in other common types of like fingerprints, oils, greases, and things like that that could alter the data. Now I want to go through a couple experimental considerations that we made. The first was the use of unpopulated boards. Firstly, the components will impede the transport of the solvent over the surface of the board. The idea is that we want to make a completely uniform coating, and putting components on the board will keep the solvent from moving evenly across the board. The second is that if we add components, we have to solder them down, and then that will inherently add some amount of contamination that we can't control for. The next is choosing the sample locations to be as far apart as possible. On the previous slide, you noticed how we made a kind of a triangle, and we picked those spots intentionally because the idea is that we coat the entire surface of however large of a board we want to be completely uniform across the entire board. The next point is the solvent selection. It's very important that the solvent that we choose have 2 key properties. The first is low surface tension, and for that we can't use water. And I can see this demonstrated on the right-hand side of the screen in that picture, where we have 3 different solvents spread out on the surface of the boards that we use. It's the same volume of solvent, but you can see how the IPA and the hexane have spread out nicely and they've wet the board, whereas the water kind of beads up and it doesn't wet out to the board. And that's going to cause an issue because we want it to wet out to the board and create this even surface. The second property that the solvent must have is that it needs to have a high solubility or be able to dissolve whatever contamination we're using. In this case, we chose sodium chloride, which unfortunately has a very low solubility in IPA. So we could not use IPA for this study. And for that reason, we chose methanol, because methanol has a very similar surface tension, very low surface tension, but it can dissolve about 1,000 times more sodium chloride than the IPA can. The last selection was the contaminant that we chose, or the contaminants. Like I said, we chose sodium chloride and PDMS because these are very commonly looked for components when failure analyses do these IC failure analysis work. All right, so let's look at the data for the uniformity of the spin coating. So in the charts we see on the left, we see the C3 response. In the middle chart is the IC response, and on the right we see the FTIR response. The error bars in each case represent the standard deviation across all the different points on the same board. So the bigger those standard deviation bars are, the farther or the less uniform we were able to get that sample. So first of all, we notice that each measurement has its own different uniformity levels. For example, the average standard deviations, or those error bars in the C3 results, show they're about 13% of that largest measurement. Now, that's pretty big, but that makes sense because C3 is not really designed or good for quantifying concentrations of solutions. It wasn't designed to do that, and no one uses it for that. So that makes sense. However, if we take those exact same solutions and analyze them via IC, we see that the standard deviation is only about 3% of that largest measurement. So it's much smaller. And we can see the standard deviations in the plot there are, the bars are almost smaller than the sizes of the points themselves, which means that we are able to homogeneously coat that board and get the same concentration across the entire surface. Now, if we compare that to FTIR, we see similar results, something in between the IC and the C3, where we see a standard deviation of about 7% of our largest measurement. Now, this is probably due to the semi-quantitative nature of that technique, having to do with the pressure of having to measure those on the ATR crystal. But regardless, the results show that it's somewhat uniform and could be used if needed. All right, so the next part is the linearity of the data. And the linearity leads to the part about being able to put a precise amount down on the board. So with the exception of one board, the response of each of those techniques is very linear with respect to the concentration of the boards. And this means that we're able to pick and choose which concentrations we put down. So all we'd have to do is create a calibration curve like what you see on the screen, and then say, okay, well, if I want to go to 10, if I want a surface concentration of 10 micrograms per inch squared, all I'd have to do is move over to my calibration curve and say, okay, I need to use a solution concentration of maybe around 3.5 grams of sodium chloride per gram. So what we've shown is that we can both precisely contaminate our boards and do it uniformly over the entire surface. All right, so in conclusion, when you're attempting to coat PWBs with a uniform contamination layer, the choice of solvent is very important. Remember, we need to have both high solubility of the contaminant in our solution, and we also need to make sure that we have a low surface tension in order to completely wet the surface of that PWB. There are other coating methods available that we've tested, but spin coating seems to show the best performance, and that makes sense given the physics and the mechanisms of how that technique works. Also, keep in mind that there are two different methods for creating different surface concentrations when using spin coating. The first, which is what we did, was to change the concentration of the contamination in the solvent. So use 3 or 4 different contamination levels in the solvent and use the same spin coating parameters. But you can also change the rotational velocity and use the same solution to create different surface levels. So the faster you spin the sample, the thinner that layer is going to be and the less contamination will be on the board. All right, so next I'd like to go over some frequently asked questions on this topic. So the first is spin coating the only coating method available? The answer is no. There are other methods available like dip coating or spray coating that you can use, but make sure that before you do that, you assess the uniformity and linearity like what we've shown in this work here. The second question is, what if I can't use an organic solvent like methanol or hexane? Maybe there's health issues or OSHA requirements or whatever the requirements are. If you can't use those types of solvents, you can consider surface modification techniques, something like plasma treatment or a chemical etching, which will increase the surface energy of the substrate and help the solvent to wet out. Also, different mixtures of solvents can be used to help provide a balance between solubility and surface tension. For example, if you use a solution of IPA, which is a low surface tension, with maybe 5% water, you're going to raise that surface tension a little bit, but you're going to dramatically increase the solubility of various contaminants, ionic contaminants in there. The last question is, what are the spin coating parameters I should use? That's a great question, and it really depends on your application. But a good starting point would be to try 5 milligrams of sodium chloride per gram of solvent and put your spin coater to about 500 RPM and let that rotate for about 30 seconds. That should put you around the 10 micrograms of contamination per square inch. And then you can go from there, tweaking the parameters, either going faster or slower in your rotations or increasing or decreasing the concentration in your solvents. All right, with that, that's everything. I hope this is useful to everyone on the call. Thank you for your attention, and we look forward to seeing you at the next Tech to Tech series. And with that, I'll pass you back to William. Thank you.
Thanks, Adam. Thank you guys for watching this Tech to Tech session. If you'd like to discuss this topic further or have any questions not answered in the session, please contact your local KYZEN regional manager or send an email to tech@KYZEN.com, and we will have someone follow up with you as soon as possible. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.